Okay, this is the last problem on the pendulum, and I figure I would go to a playground and take my son along and film him, and I posted that video. And in the video I counted that he made 20 swings in 58 seconds. So t equals 58, and I guess I could call this here n, maybe. N, that was supposed to be an n, oh boy. N equals 20 swings, and then t equals 58 seconds, and you can confirm that. And of course, when I divide 20 into 58, I'm going to come up with what the period is of this pendulum, 2.9 seconds. Notice that I only have two significant figures. I have to keep that in mind. And let's say on this for the swing, I want to figure out what the length is for that pendulum. As I said in the video, I measure it to 2.0 meters. However, I noticed that the chain links, they of course have some mass too, and I measured it from pretty much the pivot to kind of where my son's abdomen is, and so I came up there with pretty much exactly 2.0 meters. But you know, because the chain has some weight too, maybe that's actually a little bit higher. So I would say let's figure out what the length is, given that we know we're in Alaska and gravity is 9.82, and we know what the period is because we look at the video and we count the swings. And then again, I kind of looked at it that it has a length of 2.0 meter, and that's what I want to confirm. I'm going to pull this over here, there. And that of course means that I need the pendulum equation again. So t equals 2 pi square root of L over G. There we go. And this time around I solve for the length L. As I said, I want to confirm that result here, and that when you do the algebra on this one here, is going to come out to t squared times g divided by 4 pi squared. And again, you can see it when you do the algebra yourself. And when I plug in numbers, I come up with 2.1 rounded, I believe. Yeah. And I only have two significant figures, so 2.1 meters rounded. So that pretty much means that my measurement was correct, and that maybe his weight, he's in the neighborhood of like 50 pounds or so, is quite a bit more than what the chain links add to that. There's a problem about the gymnast, and it says a gymnast does a one-arm handstand. The humerus, which is the upper arm bone between the elbow and the shoulder joint, may be approximated as a 0.30 meter long cylinder with an outer radius of 10 to the negative 2 meters, which means that's 1 centimeter, and a hollow inner core with a radius of 4 times 10 to the negative 3 meters, so that's 0.4 centimeters. Excluding the arm, the mass of the gymnast is 63 kilograms. What is the compressional strain of the humerus? By how much is the humerus compressed? Okay, so we have a gymnast who is supposed to make a handstand, I guess just on one arm. And then this here would be the bone. I realize that this is a femur, but what it does show me is that it's hollow inside, and therefore the part that has to withstand the stress is this part here, kind of like a tube around it. And so that means that when we calculate the area on this one here, it becomes a little bit difficult, just slightly. We'll see. Okay, in any case, what we have given is the radius. Actually, there are two of them that we have given, and they in turn will then give us the area, the cross-sectional area. So we figure that this one is given. Then her mass is given, which means that of course her weight is given as well. So mass, and therefore also her weight is given. Let's see, the length of the humerus is given as 0.3 meters, or pretty much exactly 1 foot, and I want to say that's it. And I'm going to look up the equation, and we have to look at the equation for elastic deformation, which says F equals Young's modulus times delta L divided by L 0, so that actually should be an L0 here, times the cross-sectional area. And then I would still have to write in my table that, well, the Young's modulus is given, we just look it up in a table in the book for bone, and the delta L over, that's actually asked for in the second part of the problem. So delta L is what they're asking for in the second part. In the first part, they just ask about the strain, which is this one here. So when we do the algebra on part A on this one, it's going to be delta L over L0 equals the weight. I guess I could also call this the weight here. Well, actually, not normally, but in our case that's the case. So 63 kilograms times 9.8 divided by Young's modulus, which you find in the book for bone to be 1.2 times 10 to the 10th Newton per square meter, and then the area, and then that equals, and whatever that result is, and that will have no units because this is length divided by length, or if we look at the units here, you'll see that they all divide out. Now, what is the area? Well, the area of the cross-sectional area is this entire circle here minus the inner circle. So the way this area here can be calculated is A equals pi r squared, the outer. Let's see, is that what they call it? Do they call it outer radius? Yeah, that's what they call it, the outer radius, squared minus pi times r, the inner radius. So this part here is of course the hollow part being subtracted, so that really it's just the bone that comes out for the area, and that's what we have to plug in for the area, and then everything else given. Of course, it comes out to a very small number. For one, of course, the y is a very large number in the billions, so that's why the overall ratio is going to come out really small. And then of course, yeah, it's her bone, and we can imagine that bone is not being compressed that much. So part B then is simply going to be delta L equals L0, the original length of 0.3 meters, times the strain that we have just calculated here, which of course is that result, so times that strain. And that of course will be in meters, relatively small number, in the neighborhood of a few millionth meters or so, so just a fraction of a millimeter by which it is compressed.